essentially what I still have to finish is the chapter 10. So we discussed already section 10.1 and 10.2. Okay, so we are discussing parametric curves, which are given by a set of parametric equations where t is the parameter. Normally, you can think about the time, and t will be in a certain range from a to b. Now, our main goal is to generalize everything we have done so far to this new situation where a curve is given, where we have a parametric curve, where a curve is given by parametric equations. So last time we saw already, okay, if you want to compute a tangent, maybe I should stress once more, of course, one way to solve questions related to a parametric curve would be, okay, you try to eliminate the parameter, which is possible in some cases. And once you eliminate the parameter, you are just, the situation which you encounter is just the situation which we have discussed previously. So maybe you, in some cases, maybe you can write y as a function, capital of f of x, and then you just use the approach we have used before. But for some cases, it is either complicated to eliminate the parameter. So in some cases, it's possible. We saw last time an example, the so-called cycloid. In case of cycloids, the parametric equations are quite easy. And indeed, it's possible to eliminate the parameter. But the resulting expression would be quite complicated and not so convenient to work with. Or it's not possible to, or it's not obvious how to eliminate the parameter. In such situations, okay, we want to have, for instance, if you want to compute tangents, we want to have an expression which just involves those two functions, f of t and g of t. And last time we saw, okay, that for the tangent, actually we can think about, we consider this expression here as a fraction, and we multiply the numerator and denominator by 1 over dt. So you can think about, you do this here. Now, so this tells you that you can compute the derivative as, okay, you take the derivative of g and divide it by the derivative of f. Okay, and this does not involve here. This just involves here f of t and g of t. So you do not have to eliminate the parameter first in order to find the derivative here. So we saw this last time, and also for the area. So if g is larger or equal than 0, and t is in some, for instance, from a to b, then you get here a curve, and this curve has an area below the curve and above the x-axis, and we saw last time how to compute the area. Now, the next question we want to consider is the arc length. Okay, so we know already that if we have a curve given by such an expression where x is between a and b, maybe let's write here alpha and beta just to make it different here from this a and b. Okay, then we know already that for the arc length of this curve here, we have the formula, the integral from a to b, and then we have the square root 1 plus dy over dx square times dx. That's the formula we derived previously. And now you can think about, okay, now the curve is given by parametric equations, but you cannot easily write it in this form here. So we want to have a similar formula. So we assume here in addition, so this I can delete here. Let's assume in addition that the derivative of x with respect to t with respect to the parameter, which is just the derivative of f, is larger than 0. Okay, which means that if as t is moving from alpha to beta, x is increasing. In particular, under this assumption here, the curve is only traversed once as t goes from alpha to beta. But we will see in a minute why we need this. Then at least formally, we want to, our main goal again is to express this formula. So this formula would involve the derivative here of this function f, which we cannot easily find for our parametric curve. And we want to have a formula which just involves those two functions here, small f of t and small g of t. Now, just formally, okay, what you do is you use substitution. So I first write the integrand. So you have here dy over dt over dx over dt square. Okay, and then here you write dx over dt times dt. Okay, so it's kind of, you use the substitution rule. So now you have to integrate, because the new variable over which you integrate is t, so t has to go from alpha to beta. Okay, so now you see that, okay, you can take this under the root and it becomes the square. And here you need that dx over dt is positive. Otherwise, you have to replace this here. Otherwise, taking this under the root is only possible if you have here the absolute value. So the situation is a little bit different when dx over dt is not positive. But if you take it in, you see, okay, what you get is the integral from alpha to beta, and then you have here dx over dt square plus dy over dt square dt. Okay, and here you see now the advantage of this formula here compared to this one is, okay, this one would involve the function capital F, which you might not be able to find here because you're not able to eliminate the parameter. But if you look at this expression here, okay, this expression just involves here the derivative, just those two functions here, the derivative of this function square plus the derivative of this function square. So if you have given a parametric curve by parametric equations, okay, you're going to use this formula here. But as you see, of course, this is not the exact proof here, because I treat here dy over dx as a fraction, and also this here, it's clear that this holds here, but I treat it as a fraction. Of course, this is not a precise proof here, and we wanna find a precise proof. In particular, we will see that this formula also holds if this assumption here is not necessarily satisfied. Okay, but this essentially is the formula for the arc length of a curve, of a parametric curve, of a curve given by parametric equations. Now, if I wanna do this more precisely, this parametric curve here is some curve. And this is our start point alpha. And this is our initial point, and this is our end point. Okay. Now, what we do is, if you want to find the arc length, so essentially you should see it like this. The formula which you saw here. Okay, I'm going to prove it now exactly. What we have to do, or one way to find the length of this curve here would be, okay, you divide now the interval from alpha to beta into subintervals, n subintervals. So you have then here a point. So this is then t0. You have here a point t1, and then you have here, for instance, a point t2. You have here a point t3, and so on. And this one here is tn, and you have here a point tn minus 1. Okay, and then you replace the original curve by a polygon. Okay, so you replace the original curve here by the polygon which connects those 2 points here. Then you connect those 2 points, then you connect those 2 points, and so on. And as a first approximation, you are going to compute the length of the polygon instead of computing the length of the parametric curve. And this will give you, okay, so for the arc length, you will get the approximation. You have to sum up over the lengths here. So what you have is, okay, so if we denote this point here by p0, this point by p1, this point by p2, this point by p3, this point by pn minus 1, and this is the last point pn, then what we have to do is, okay, we have to add up all the distances between those 2 points. Okay, and then, so we have here a certain subdivision of this interval, and then we let t tend to infinity. And in the limit, we will get the arc length. Okay, so the arc length will be the limit n tends to infinity, sum I from 1 to n, and then the length of the line from pi to pi minus 1. Or the other way around, it doesn't matter. It's actually something which we have to prove, because we have already, for certain curves, we have already defined the arc lengths, and this is another way to compute the arc lengths, but which is pretty much the same as the previous approach. So this will give you here the same expression. Now, okay, so now you just write out here this here. Okay, so this is the square root. Now you have the difference between the y values. So what you have is the difference between the y value squared plus the difference between the x value squared. Okay, so the delta xi is equal to, so what you have here is f of ti minus 1, f of ti minus f of ti minus 1, and the delta yi is g of ti minus g of ti minus 1. Now you see that if the functions here f and g are sufficiently smooth, then whenever you have something like this here, okay, and in particular the ti minus 1 and the ti, as the subdivision is getting finer and finer, those points here are moving to each other. So what you have is, okay, a difference of 2 function values, and in such a situation, we always think about the mean value theorem, which tells us, okay, how large this difference is in terms of the derivative. Now, so if f and g are sufficiently smooth, then you will have here, by the mean value theorem, this will be equal to the derivative of f at some point, which is between ti minus 1 and ti times delta t. Okay, and the delta t here is constant. So this here depends actually on the point, but the delta t does not depend on the point which you choose, because we are going to divide the interval from alpha to beta into n subintervals, all of them the same size. Okay, so this is here by the mean value theorem, and similar if g is continuous, if the derivative of g exists, then you can find here a sample point, which is not necessarily the same, such that this is equal to the derivative of g at this point between those two here times delta t. Okay, now you see this is useful, because now you can write this square root as the square root of the derivative of f at this point here, square, plus the derivative of g at the other point, square, and delta t, you can take it out. The delta t is positive, so there's no absolute value here. So you see the expression with which we end up with is, okay, we have the limit, n tends to infinity, and then we have the sum, I from 1 to n, and then we have the square root. Here we have the delta t. Here we have the derivative of f at the sample point, square, plus the derivative of g at the sample point, square. Okay. Now, this is, strictly speaking, this is not a Riemann sum which we have here, because for a Riemann sum we have a function evaluated at some sample point times delta t, but we have here 2 different points. Okay. So, strictly speaking, it's not immediately clear that this is equal to the integral here, so that this is equal to the integral from alpha to beta, and then the square root dx over dt square plus dy over dt square dt. It's not immediately clear, but since those two sample points, okay, this one and this one are both in the interval ti minus 1 to t, from ti minus 1 to ti, and ti is, as the subdivision is getting finer and finer, those 2 points are moving towards each other. So it should be clear that if those two derivatives are sufficiently smooth, this will be true here. And in particular, we have to assume that those two derivatives here are both continuous, because otherwise the integral here would not exist. But if those two functions are continuous, okay, it's easy to see, or at least at this stage, it's easy. I guess everyone will believe me that this here is equal to this integral here. It's almost the same as the situation where you replace this point by this point, or the other way around. If in particular, if those functions are continuous. So, and this is the same formula as the one which I derived before by using this not precise approach. What we need here is if the derivative of f and the derivative of g are continuous on this interval here, then the arc length will exist, okay, or we can define the arc length, and the arc length is given by the formula, the integral from alpha to beta, and then the square root of dx over dt square plus dy over dt square dt. Okay, and you see that also this formula is easy to memorize. You can think about, you take this in, and then what you get is the integral from, so if you take this in here, this will cancel with this one, and you have the integral dx square plus dy square, which we call ds. Okay, so it's the same rule. You if you want to compute the arc length of the curve, what you do is you integrate from alpha to beta over the arc length element ds, and the arc length element you compute by looking at the right triangle, where this length here is dy, this length is dx, and this here is our ds. And the theorem of Pythagoras holds for this right triangle. So that's the way you can memorize this formula. Now, maybe let's look at a very easy example. Let's test the formula by looking at the circle. Y is equal to r times the sine of theta, where our theta is between 0 and 2 pi. So this will give the circumference, the usual formula for the circumference of the circle. Now, you see that, okay, so in this situation, dx over dt is equal to minus r times sine of theta. dy over dt is equal to r times the cosine of theta. So if you plug this in, then you see that the arc length is equal to the integral from 0 to 2 pi. And then here, so what you see is you have just the square root of r square dt. Okay, so what you get is the usual formula for the circle. You see this is kind of slightly more easier than using the usual expression for the circle where x squared plus y squared is equal to r squared. Slightly more easier. Because if you use the usual expression, what you're going to do is you plug in the formula, and you have to do some simplification. Eventually you will also end up with this here by doing a substitution. But you see that this is kind of preferable over the approach which we have seen previously. You also see here that, okay, if you because this is walking around the circle once, but if you walk around the circle twice, okay, so the only difference will be here, and you see you will get twice the circumference. So actually, this formula here, okay, is also true if we do not only traverse the curve once. If we traverse the curve more than one times, okay, this formula is still true, okay, but we'll compute the arc length of the polar of the parametric curve, okay, not of the curve which we are seeing. last time I already stressed that the parametric curve is different from the curve if you draw it, okay? Because if you look at this one, okay, it looks the curve is just a circle, but the parametric curve is twice the circle. You run around the circle twice, and you have a direction as well for the parametric curve. Assume you have this one, x is equal to cosine square of theta, and y is equal to cosine of theta times the sine of theta. And theta is between 0 and pi. Okay, so the question is, as theta runs from 0 to pi, what is the arc length of this curve? Okay, so even so, if we cannot imagine this curve, we still can just use we just can employ a formula. So dx over d theta is equal to twice the cosine of theta times minus the sine of theta. Now dy over d theta, maybe it's better to write the second function. So theta between 0 and pi. Maybe it's better to write this as, just for taking the derivative, it's more easy to write this as 1/2 the sine of 2 theta. Then you see, okay, that this derivative here is, okay, so the cosine of 2 theta. And then you have, from the inner derivative, this one cancels here. So you see that in order to use the formula, you have to compute this one. Okay, but you see that this one here is the sine of 2 theta squared plus the cosine of 2 theta squared, which is equal to 1. So the formula gets very simple here in this case. So you see that the arc length of this curve here from 0 to pi, the square root of 1, because of this expression here, d theta just equal to pi. Okay, this is not a surprise because this curve here, even though it's not so easy to see from this expression here, but this is just a circle. Okay, just shift it. So you have, if you compute x minus 1/2 square plus y square, okay, so you see that you just plug it in here, the expression. So you see for the first one, you get the cosine to the 4th theta minus cosine square of theta plus 1/4 plus and for this one, so let's use this expression maybe, cosine square of theta, sine square of theta. Okay, so you see that this what you see here, equal to 0. Okay, because if you look at those two here, you can take out the cosine square of theta, the rest is equal to 1, and this will cancel with this one. So it's equal to 0, so what you get is 1/4. Okay, so actually the curve here in it's possible to eliminate the parameter here, and what this and the curve here is again the circle, but the center is different. The center is at the point 1/2 0. Now, also in our textbook, you find an example where the arc length of the cycloid is computed. I will skip this and go directly on to the surface area. We know that the formula for the surface area is somehow similar to the formula for the arc length. So if you have a function given by such an expression, which is assumed to be larger or equal than 0, and x between a and b, and if you rotate this function about the x-axis, then you get the solid of revolution, and we found the following formula for the area, for the surface area of the solid of revolution, namely the integral from a to b 2 times pi times y, and then the square root of 1 plus dy over dx square dx. Okay, so this is the surface area of the resulting surface of revolution. Now, again, you can do the same reasoning as I have shown you before for the arc lengths, and you will get that, okay, if our curve is given by parametric equations, so if we have a parametric curve, then the same formula more or less holds. So you can again think about it. You replace this here by dx over dt times dt. You write here dy over dt, here dx over dt, and you multiply it in. Then what you get is, okay, so here we have the integral from alpha to beta, and then 2 times pi, so y you replace by g of t. And then you have the square root, the derivative of f of t square plus the derivative of g of t square dt. Okay, so, but actually, again, this is not a proof. So in order to find the precise proof, we need here some assumptions, namely, this must be larger or equal than 0. Also, the curve should only be traversed once, that we have, that this question here makes sense. Then, under this situation, if you rotate the parametric curve about the x-axis, you can use this formula in order to compute the surface area. And of course, the formula is easy to memorize. You just use this formula and think about the dy. You multiply here this fraction, both enumerator and denominator, by 1 over dt. And here you write dx over dt times dt, and you plug it in. And you put the dx over dt under the square root. For this formula, we know already, okay, that the way to memorize this is, okay, so we have 2 times pi times y times the arc length element here. Okay, so for instance, if you look at an example here, okay, we take this parametric curve, we rotate it about the x-axis, where we consider the range of parameter t from 0 to 1. Now we want to have the surface area of the resulting solid of revolution. So what you have to do is just plug in here. So a is equal to the integral from 0 to 1, 2 times pi. So here you see the g of t is y, so t square times the square root. Now the derivative of f, which is 3t square plus 2t square dt. Okay, now so this gives the integral from 0 to 1, 2 times pi times t square. Now you see you can take out here t square, so you have here t to the cube. And what remains then is the square root of 9 t square plus 4 dt. Okay, this integral easy to compute. You substitute this here. Okay, because here you have t square times t. So if you call this here u, then you have here the square root of u, and this one you can replace by u minus 4 over 9, and this here will cancel out from the inner derivative. Okay, so but I don't have to do this because this is standard by now. So you see that, and once you have done this, it's easy to integrate. If you have a parametric curve, this is one example you'll find in our textbook. So it's kind of, because we will discuss this next semester, so maybe we can take a look at it already now. An important issue is, okay, can you find a measure which helps you to measure how curved the curve is? So you have, for instance, if you think about this curve here, y is equal to x squared, parabola. Okay. Now, what we want to do is we want to find a measure which tells us, okay, how curved is this curve. Okay. Now, what do I mean by this? How curved is the curve? So, for instance, you see that in this point, if you're standing in this point, okay, if you do not see a coordinate system, you're just standing in this point, okay, and you're walking around the curve, okay. Here, in this point, you will feel that the curve is very curved. Okay, so you have to walk like this here. But if you're here, you will feel, okay, the curve is almost like a line. Okay. So if we find the measure, okay, the measure should, for here, it should tell us, okay, the curve is not curved very much. Okay. But here, the measure should tell us, okay, the curve is very curved. Okay. This is something we are going to discuss next semester. Now, you see that roughly for something which describes how curved is a curve, second derivative, okay, because the second derivative tells us something about the concavity behavior. So roughly we would think about, okay, the second derivative should tell us, okay, how curved is a curve. Okay, but if you look at the second derivative here, okay, then the second derivative is constant too. So this tells us something about the concavity behavior that's right of this curve, but it doesn't reflect what we want to have from a measure which helps us to measure how curved is a curve. Okay, because here this measure should be large and here this measure should be small. That's why in mathematics we call something which is called the curvature. The curvature is a measure helping us to understand how curved is a curve. Okay, so and the curvature is defined. If you see this for the first time, you might think it's a little bit strange. So what we do is, okay, we look at some point. Now we look at the tangent, and we look at this angle here. Okay, and we define the curvature. So the curvature is the change of this angle here with respect to the arc length. So the curvature will be defined by this expression here. So in our textbook, you see one example which asks you to discuss this curvature. We will the reason why this is a good measure for how curved the curve is, we will discuss next semester. Now, in our textbook, you find the example, okay, for a parametric curve, okay, proof that the curvature can be computed by the following formula. I told you already last time that in applications, engineers like to, if you take the derivative with respect to the time, they like to use the notation where they write a point on top of it, which means derivative, taking the derivative with respect to the time. Okay, so that's why I will use this notation here. So this is x point, y double point minus x double point, y point over x point square plus y point square to the 3/2 for a parametric curve. Now maybe let's check why this is true. You find this at the end of section 10.2 as one of the exercises, one of the last exercises. So prove this formula here for a parametric curve. And this is the definition of the curvature. Okay. So first we have to express this angle here. Now how can we express this angle? This angle is the arctangent of dy over dx. Okay, because you see that this is the tangent. Okay, so the slope of this tangent dy over dx, and if you take the arctangent, you get here this angle. Okay, now we compute. We have to compute the derivative here with respect to the arc length. S is the arc length. Okay, the reason why we choose the arc length here is not mentioned in the example which you find in our textbook, but the reason will become clear next semester. Normally, we will use quite often, if we parameterize such a curve, the parameter which we are going to use is quite frequently the arc length. The reason for this is that if we choose the arc length, the parameterization will be is kind of independent of the coordinate system. We will learn this next semester. So what we have to do is we have to compute the derivative with respect to the arc length, but let's first compute the derivative with respect to the parameter t, where this is the parametric equation describing the curve. Okay, so you see that in order to do this, you have to use the chain rule. So you have 1 over 1 plus dy over dx square for the outer derivative times the inner derivative. Now for the inner derivative, we know already that, okay, if we have these parametric equations here, we know already, okay, this is nothing else but y point over x point. Okay, the point is, once more, the point is taking the derivative with respect to t. Okay, we saw this formula for the tangent, because this is the tangent for a parametric curve, so we have to compute now d over dt of y point over x point. Okay, here we use the usual formula, so this is y 2 points, x point minus y point, x 2 points over x point square. For this we can also write y point over x point, so this becomes y 2 points, x point minus y point, x 2 points over, and here we have x point square plus y point square. Okay. Now, just to remind you, the arc length, okay, can be computed as we just saw the formula as the integral, and then we have x point square plus y point square dt. Okay, so from the fundamental theorem of calculus, we know that the derivative of this function here with respect to t is just this function here. So it's x point square plus y point square. Okay, so the curvature, which is the absolute value of d phi over ds, is equal to the absolute value. Now, because everything is in terms of dt, okay, so what we do is we write d phi over dt over ds over dt and plug in those two expressions here. And what we get is, okay, so this is y 2 point, x point minus y point, x 2 point over x point square plus y point square to the 3/2. So this is the curvature. If you use this definition, this is the curvature of a curve given by parametric equations. So if we have a usual function, a usual mean the function given by this expression here, then we know that one possible parametrization is x is equal to t and y is equal to f of t. So this is a parametrization of this function here. So this formula here for the curvature can in particular be applied to such functions. What do we get? We see if we differentiate this here twice with respect to t, then this will be equal to 0. Okay, the first derivative with respect to t will be equal to 1. So, and this here will be the second derivative of the function f. So what we have here is the second derivative of the function f over, and then we have here 1 plus, and here we have the first derivative of the function f square to the 3/2. Okay, so for a usual function, okay, function in usual sense, the curvature is given by this expression here. This somehow fits our intuition because I said that roughly speaking, the second derivative should measure how curved is a curve. Okay, and you see this indeed depends on the second derivative. Now, let's just check this. Also, this is an example in our textbook at the end of section 10.4. So you see that if f is linear, a linear function, okay, is not curved at all. Okay, so the curvature should be equal to 0 if the curvature makes sense. And you see that this is equal to 0 indeed. So you see the curvature is equal to 0 for a linear function. If you consider a circle with radius r, so here you have to parameterize the circle by the usual by this usual parametrization. Okay, now you cannot use this formula here. You have to use the previous one with the points, x point, x double point, y point, and so on. So you use the usual formula and you get kappa is equal to, what would you guess? A circle with radius r. If the radius is very small, is the circle more curved than if the radius is large? You understand what I'm talking about? If the circle, so if you walk along a very large circle, okay, you do not feel a curvature, okay? It's like, if the circle is very, very large, it's like you are walking on a line. Okay, you will not feel that the circle is curved. But if the circle is very, very small, okay, you will feel that the circle is very curved. Okay, so, and the answer is 1 over r, which makes sense. If the radius is very small, the curvature will be very large, meaning that the circle is very curved. Okay, and you see that, if you apply this here for the function, not linear, but y is equal to x squared, what do you get? So you see this is equal to 2 here over, and here you have 1 plus 4x squared to the 3/2. And this function here, if you plot the graph of this function, of the curvature, then you will see that, okay, because at 0 you have a maximum 2, and as x tends to plus infinity and minus infinity, you see this expression tends to 0. Okay, so, and it's symmetric, so you can roughly, okay, it looks like this here. Okay, and if you compare this here with, you see this now fits our measure, okay, because I said that if you are standing on the parabola, here the parabola is very curved, okay, much more curved than here, okay, and you see indeed at 0, okay, this means you are standing at 0. The curvature is maximal, okay, so here the curve is most curved, and as you walk in this direction and this direction, the curvature will get to 0, will tend to 0. Because now we go on to the section 10.3, and what we want to do next is we want to pick out one of those parametric curves, a class of parametric curves, and we'll study them in more details. Now this is, for this we have to introduce another way to represent points in the plane. So the usual, the way we have used so far in order to represent points in the plane is by using so-called Cartesian coordinates. So what we do first is we fix two lines which are orthogonal perpendicular to each other and are the coordinate system, and we measure and if we have given a point, so what we do is, okay, we represent the point by two numbers, namely the reflection on the x-axis, so this one and this one. So this is called Cartesian coordinates. But this is not the only way to represent points in the plane. There are also others, and one important other way to represent points in the plane is so-called polar coordinates. So what we do is it's quite different from here. So here we fix two lines which are orthogonal, and those two lines form our so-called Cartesian coordinate system. Now, another way to do this, to represent points, is not fixing two perpendicular lines, but fixing one point and a half line. Okay, so you fix one point, call it O, and you fix a half line. Now this point is called the pole, and this line is called the polar axis. And if you have given a point P, then we use a different way to represent the point, namely we connect the point with the pole. Okay, and we again use two numbers in order to represent the point, namely the length here of this ray, which we call r, and the angle between this ray here and the polar axis. So this is another way to represent every point in the plane, and this representation is called, or these coordinates are called polar coordinates. Now, you see already that, for instance, here you have a problem for one point, because one point we have to discuss in extra, which is the pole, okay? Because the pole does not have a r, doesn't have an angle. So the pole has the radius 0, but does not have an angle, okay? So for O we use not only one angle, but we allow any angle as polar coordinates. So the polar coordinates of the point O would be 0 theta, and theta is any angle. Okay, so you see that the pole has many, many representations. This is already a big difference between those two ways of representing points. Here the coordinates you get are unique, but here the coordinates are not unique. You get many more, because you can add to, also for another point which is not necessarily the pole, you can add to theta a multiple of 2 pi, and you will get the same point. Okay, so one point does not only have one representation, but many. Now, apart from the polar representations we get by using what I said so far, we also allow polar representations where the first coordinate is negative, so minus r and the theta. And which point do we mean by this? You have fixed the pole, you have the polar axis. Now, so the r here is larger or equal than 0. Okay, so if you look at the pole r theta, not minus r theta, okay, then maybe you get this one. Okay, so let's say this is the point, I should call it P prime, which has polar coordinates r theta, not minus r theta, because this point I have to define. Okay, which point is this? Now, what we do is, okay, we extend this ray, okay, in this direction, and just use the same radius here once more in the other direction. So if this is r, this length here will be r as well, and this point here will be our point having this polar representation, these polar coordinates. Okay, so we also allow, as possible polar coordinates, we allow also that the first coordinate is negative, but we interpret the point suitable like this here. Okay, so if you have given, for instance, -1 and pi half, then the point will lie here. Okay. So if you look at Cartesian coordinates, if you identify the polar axis with the x-axis and the pole with the center of the Cartesian coordinate system, then the points -1, pi half in polar coordinates will correspond to the points 0, -1 in Cartesian coordinates. Okay, and you see like this that the price you have to pay here for this new coordinate system, or this new way of representing points in the plane, or what is different to the Cartesian coordinates, is that one point can have many different representations. So the representation of a point in polar coordinates is not unique. But we will see, of course, this is a disadvantage, something which you don't want to have from a coordinate system. But we will see still the polar coordinates are important, and for some examples they will greatly simplify computations. Okay, so, but you see that one point has, if you have a given point, and the point has the polar coordinates r theta, the point will have many other polar representations or many other polar coordinates, namely also you can add to theta a multiple of 2 pi, so also r theta plus 2k pi, where k is any integer will represent the same point, but also minus r and theta plus 2k pi plus pi will represent the same point. So you have many representations for the same point in the polar coordinate system. Of course, you can once you have given, for instance, the polar coordinates of a point, you can compute the polar coordinates of the the Cartesian coordinates of the point where you identify the polar axis with the x-axis, and the pole becomes the origin of the Cartesian coordinate system. So this is essentially the way you so this here is r, this here is x, this here is y, and here we have theta. The way you compute or you convert polar coordinates into Cartesian coordinates and the other way around is just by looking at this triangle here. So you see that, for instance, if you have given polar coordinates of this point P here, so from polar to Cartesian coordinates, okay, you have the formulas x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So this is from polar to Cartesian coordinates, and the other way around, if you have Cartesian coordinates, you want to compute the polar coordinates, what you use is the relation r squared is equal to x squared plus y squared, and theta is equal to the arctangent y over x. Now, you see that since for r we just have two possibilities, plus or minus, but here what you get actually is the representation of P as a in polar coordinates where the first coordinate is positive. So here you will choose for r the square root. But for theta, because for a given value here, you will have here different solutions, which all make sense. So whereas given the polar coordinates, if you use this in order to find the Cartesian coordinates, of course you get the unique solution. But here you get different solutions, and only one of them might be the correct one. So you have still to, if you convert Cartesian coordinates to polar coordinates, you have still to think about which one of the thetas, because you might get here, you will get here different solutions or different values for theta, and you have to think about which one is the correct one by looking essentially at the sign of x and y. Because then you know in which quadrant the point is, and this will be enough to figure out which one of the angles is the correct one. Okay, so this is converting polar coordinates into Cartesian coordinates and the other way around. So the reason why we look at polar coordinates is because we want to discuss so-called polar curves. Now, a polar curve is a curve which is given by an expression like this here, or more general, also sometimes implicitly, like this here. Okay, but where you interpret r and theta as the polar coordinates of a point. Okay, so the points which are lying on such a polar curve are all the points which have at least one, because the polar representation is not unique. Okay, so one point has many representations in polar coordinates. Okay, but if one of those representations, okay, satisfy this equation, then we say that the point is on this polar curve. Okay, and the curve which is traced out by an expression like this here is then called the polar curve. And in the sequel, we want to discuss such polar curves. In particular, we want to do calculus with them. Okay, so we want to find out, okay, if you have given a point on the polar curve, how to compute the tangent, or if the polar curve, for instance, is larger or equal than 0 and theta runs along. Theta is inside some interval, okay, then you get an area, and you want to know, okay, how to compute you get a region, and the question is how do you compute the area of this region? So we want to study questions like this. But first we should maybe get a better feeling for polar curves. The most easiest polar curve is maybe this one. Okay, and you see that the curve here, the curve here is the circle. So you see that this is already an advantage of the introducing a new coordinate system, where in Cartesian coordinates the circle has equation x squared plus y squared is equal to 1. The defining equation of a circle in polar coordinates gets very, very easy. R is equal to -1. Notice that R is equal to 1. Notice that R is equal to -1 is the same curve. Okay, but because again every point has a, for instance, for let's say this point here. Okay, you can either, in polar coordinates, you can either write this point here as you have the radius is equal to 1 and the angle is pi, or you write this as -1, 0, which is the same point. Yeah. Okay, so this polar curve, how does this polar curve look like? Now, so all points on this polar curve have the same angle. Theta is equal to pi over 4. Okay, so let's use this here. Okay, and the radius can take on any number. So what we get is the whole line here. And again, it's not just the line where the radius is larger or equal than 0, because the first coordinates, because this point here, okay, can also be represented by, if the length here is 1, can be represented by -1 pi half, so has a polar representation which lies on this curve here. Okay, another example would be this one. R is equal to 2 to the theta. Okay, so what is the curve given by this polar by this equation here in polar coordinates? You see, for instance, if theta is equal to 0, okay, then this will give you R is equal to 1. So you will start here. And then as theta is growing, okay, also the R will grow. So you see that, okay, what you get is something like this here. And this will be the graph of this polar curve here. Okay, so these are some easy examples. You see the same if theta, also in this direction, okay, if theta can be negative as well. If you consider for theta all possible real numbers, what will happen here? You will go down to 0. And this is the corresponding polar curve. Now, let's maybe look at another example. Let's look at this one. 2 times the sine of theta. Now, if you want to understand how such a polar curve looks like, of course, one way to do it is you make a table. Or maybe a better way is you plot this function here where you have here theta and here r, and then you translate this into the Cartesian coordinate system. So we know that this curve here looks like this here. Okay. Now you just have to think about, okay, what is the curve doing in the, how to plot the curve now in the Cartesian coordinate system. Now you see, okay, for theta is equal to 0, okay, so we are here. The radius is equal to 0, so we are in the origin. Okay, now you think about, okay, the theta is moving, okay, and you just look what is r doing. You see that, okay, if theta is equal to pi 4, so the r will increase as theta is going from 0 to pi over 4, sorry, pi half to this point here. So as theta is going from 0 to pi half, the r will increase from 0 to 1, or 2, sorry, from 0 to 2. Okay, so now the theta is moving, and the r will move at the same time. So somehow we will do something like this here. Okay, now as the theta goes from pi half to pi, so like this here, okay, the r will go from 2 back to 0. Okay, so we will have this here. Okay, now as theta goes from pi to 3 pi half, okay, so for instance, if you're here, then you see that the r here is negative. Okay, so you have to look at the other direction. Okay, and because of symmetry, okay, it will again be this point. So as theta goes from pi to 2 pi, you will just get the same curve once more. Okay, so and you might guess the circle. So you might guess that this here is this polar curve is if you interpret it in Cartesian coordinates, it should be the circle. Okay, indeed, this is easy to verify. So if you look at 2 times y, okay, now because y in polar if you have polar coordinates, y is equal to r times the sine of theta. So this will be 2 times r times the sine of theta. But you see 2 times the sine of theta is equal to r. So this will be equal to r squared. R squared is equal to x squared plus y squared. Okay, so you see that in Cartesian coordinates, okay, if you go from polar coordinates to Cartesian coordinates, this curve, okay, is given by x squared plus y minus 1 squared is equal to 1. Indeed, it's a circle. Okay, and you can also go in the other direction. Okay, because this actually, you have to be a little bit careful here when you convert from polar coordinates to Cartesian coordinates. Because if we do this here, okay, until here, we just show that the curve here, the polar curve, the curve interpreted as polar curve, is on this lies on this curve here. Okay, but it might be not the same. Okay, so you have to show also, if you want to prove that the curve given in polar coordinates by this equation and the curve given in Cartesian coordinates by this equation are the same, okay, you have to prove two directions. Okay, because indeed here, if you look at this here, you would get here 2 solutions. But those 2 solutions, one is r is equal to 2 times sine of theta. If you go back, okay, here at this point, you have 2 solutions. Because here you have this expression here. You delete r, and then you take the square root, but you can have plus minus. No, sorry, you don't get 2 solutions, but you have here actually. Maybe I should do this once. So so this was only one direction. Okay. Now, so this shows that the curve given by this equation in polar coordinates lies on the curve given by this equation in Cartesian coordinates. Now for the other direction, okay, so you just do the same, but in the reverse direction. So you will get x squared is plus y minus 1 squared is equal to 1. So this implies that r squared is equal to 2 times r times the sine of theta. So this will imply that either r is equal to theta or r is equal to 2 times the sine of theta. Okay, but this one you can forget, okay, because this one is already contained in this one, as we see here. Okay, and you really get, okay, that the curve given in polar coordinates by this equation and the curve given in Cartesian coordinates by this equation are the same. Okay, so you have to be a little bit careful here. If you convert polar curves into Cartesian curves. Okay, so this is one example. So this polar curve here is the circle. Let's maybe check another let's look at some more complicated ones. So for instance, this one. Okay, so which polar curve, which curve is traced out here by this equation? Now again, if you want to solve an example like this here, the best thing is, okay, you first plot theta with respect to r, and then you use the kind of the same reasoning as I have used here. Okay, so for this one, okay, now the usual sign, or 2 sine of theta would look like this here, but because of minus we have inverted, and then we have to shift it by 1. Okay, so this will look like this here. Okay, so this is this function here. Plotted, interpret theta and r as Cartesian coordinates, but actually the interpretation of r and theta is different. They give the polar representation of a point. Maybe I should, it's a little bit too small, so let's plot this here. Okay, so again, now if theta is equal to 0, okay, so this means we are here, then the r is equal to 1. So we start at this point here. Okay. Now you see, as theta, okay, so theta will go up like this here, okay, but the r will go to 0. Okay, so this kind of looks like. Okay, until we reach this point here. Okay, this is when the sine of theta is equal to 1/2. So theta is equal to pi over 6. So this angle here is pi over 6. Okay, so this is this piece here. Now, as we move here with theta, we move now from pi over 6 to pi half. You see that the radius is getting negative, and the smallest value will be equal to -1. Okay. So as we move like this here, because the angle is getting negative, so we have to go in this direction. Because the radius is getting negative, we have to go in this direction. So we will walk like this here. Okay, so this is this piece here, from here to here. Now, so now we are here. Now, as theta is growing from pi half to this point here, which is 5 pi over 6, then the radius will go from -1 back to 0. So we will, because the theta is going like this here, and the radius is in the other direction, so we have to plot this like this here. Now, okay, so at the moment we are here. Now, as theta is going from this value to pi, okay, the same will happen as from 0 to pi over 6. Okay, so we go here. Okay, now we are here. Now, as theta moves on from pi to 3 pi half, okay, you see that the radius is growing to 2. Okay, so what we have is, and as theta goes from 3 pi half to 2 pi, which means from here to here, the radius is growing, is decreasing from 2 to 1. Okay, and if we move on, we just get the same picture. Okay, so this is another example. An interesting example is another interesting example, which is kind of similar to this one, is r is equal to 1 plus sine of theta. Okay. Here for this example, it's a little bit different. The behavior is a little bit different because maybe I plot here. The function. So if we have this function, because this function is always larger or equal than 0, okay, the sign shifted up by 1. Okay, like this here. Should be the sign. Doesn't look like the sign, but should be the sign. Shifted up by shifted up by 1. Okay, by 1 unit. Now you see that the behavior of this curve is quite different because here you have this, you have some interval where the r is negative, but here not. So again, we start at 1. Now, as theta goes from 0 to pi half, so theta goes from 0 to pi half, the radius increases from 1 to 2. As theta goes from pi half to pi, the radius goes from 2 to 1, back to 1. As theta grows from pi to 3 pi half, the radius goes from 1 to 0. And as theta grows from 3 pi half to 2 pi, the radius goes from 0 back to 1. Okay, so like this here. Okay, so this curve is called, we encountered this curve already previously. This curve is called cardioid. Which is the Latin word for heart, because it looks a little bit similar like the shape of the heart. If you look at this polar curve, the behavior here is quite different from the curves we have seen so far. Now, as theta goes from 0 to 2 pi, you get here, you have the cosine, but twice. So twice the one period of the cosine. So what you have here is okay. So this is as theta goes from 0 to 2 pi. Now, okay. So if we plot the corresponding polar curve, now you see here, this is, so here theta goes, sorry, this is theta and r. So from here to here, the theta grows from 0 to pi over 4. Okay, so you go here from 0 to pi over 4, which is the line y is equal to x. Now, as theta grows from 0 to pi over 4, what is the radius doing? The radius goes from 1 to 0. Okay, so we start here. Now, as theta goes from 0 to pi over 4, the radius goes from 1 to 0. Now, as theta goes from pi over 4 to pi, okay, you see that the radius goes from 0 to minus 1. Okay, so as theta grows from the line y is equal to x to this line here, the line x is equal to 0, we have to look at, because the radius is negative, so we have to look at the third quadrant. Okay, so what will happen is we go like this here. Okay, so this is this piece here, from here to here. Then as theta goes from pi half to pi half plus pi over 4, okay, the radius will go from minus 1 back to 0. So we will walk like this here. Okay. Then as we go on, now the radius will grow back to 1. Okay. Then the radius will go back to 0. Then the radius will go back to 1. Then the radius back to 0, and so on. Okay, so this is what you get. Okay, now, actually this class of functions, okay, the class of functions which is given, or the polar curves, okay, are just a special case of what we have discussed before, because, okay, if you have such a polar curve, okay, you can rewrite it to a you can interpret this polar curve as a parametric curve given by the parametric equations. X is equal to, because we have here r times cosine of theta, y is equal to r times sine of theta. Okay, and you just plug this in, so you have f of theta, cosine of theta, and f of theta, sine of theta. Okay, and you can also interpret such a polar curve is just a special case of a parametric curve, where theta now takes the place of a parameter. Okay, so this means that if you have a graphing device which can plot parametric curves, it will also be able to, you can also use it to plot polar curves. Okay, you just tell the graphing device, okay, plot this here. Okay, but indeed many of the graphing devices are able to plot polar curves. Maple can do it, so I will show you this, how to use Maple in order to plot such polar curves. Now, as I told you, the plot comment in Maple is especially useful. There is also, normally, if we use packages in Maple, so because Maple has a certain amount of standard comments, but if you want to use more comments, you can open packages with the with comment. Okay, so what I need is the plot package. So if you do this, then you will see you get many new comments. Okay. And those comments will be helpful in order to plot curves, for instance, given in different coordinates and so on. Now you see one of them, if you look at this, you see one of them is, where is it? Polar plot, right? Yeah, you see one is called polar plot. So this one will be the one for plotting polar curves. Now, as I told you last time, if you do not know how to use it, what you do is you use help, then polar plot. Okay, so this is one way. Now you will get the information how to use it. In particular, how the comment is used. Normally, I just look at the examples most of the time. You see, okay, so this is the syntax. I have to study it first because I'm using the new version of Maple, and this is different. Okay. Okay, so for instance, if we want to plot for instance, let's just take this one, so the cosine of 2t. Where t is, we just saw from 0 to 2 pi. Okay, you see, okay, so our guess was correct. So indeed, it looks like this here. So maybe let's also check the other curves we have just seen. So if we use, if we look at this one, 2 times sine of t, where t is from 0 to pi. Okay, you just get a circle, but you see, if t would go from 0 to 2 pi, it's just the same, okay? But you run around the circle twice. Okay, you cannot see this here that you run around the circle twice. But here, if t is from 0 to 2 pi, you just run around the circle twice. Now, another one which we saw is this one, the hard curve. Okay, so you see this corresponds with our guess. Let's maybe. Okay, and this was the other one. Okay, also here we see. Okay, so this corresponds with our guess. We could think about here a class of curve where we have 1 plus c times, where we can change c. We already saw 2 cases of c, namely c is equal to 1, which is the cardioid, and c is equal to -2. But using a graphing device, you can also check other cases, because you see this also plotted in our textbook. So for instance, you could think about something like this here. Okay, so it almost looks like a circle, but it's like at the bottom it's a little bit, not really a circle, because at the bottom it's not, but it looks a little bit like a circle. So you see as c is moving to 0, because 0 would be the circle, okay? So if c is getting smaller here, then it looks more and more like the circle, okay? But if c is getting larger, it will become the cardioid. If c is getting even larger, then it will turn inwards, and so on. So you see that Maple is very helpful in plotting polar curves. You also see, for instance, if you have a more complicated one, like this here, slightly more complicated, it will be much more complicated to figure out how the curve look like without having access to a graving device. So for instance, if you have this here, okay, of course you could also use the same approach I just used here in order to plot this. First, it's maybe good to figure out, okay, after which interval of theta the curve will repeat itself. So when is the cosine of 8 of theta plus 2k pi over 5 equal to the cosine of 8 times theta over 5? You see k is equal to for instance, 5 would be a possible choice for this. So let's plot this curve. Okay, so you see, it more or less looks like this here, but it has much more loops. Okay, so it looks slightly more complicated. And of course, if you could play a little bit around, you could increase the coefficients, and you would get some nice patterns. Okay. But you see that actually it would not be necessary to have your own comment here, polar plot, for plotting polar curves, because you can also use this here and use the usual plot comment, but for parametric curves. So for instance, this one here, you can also plot it as okay. Use the usual plot comment. Now, last time I showed you how to plot parametric curves. So you have this kind of this bracket here. Then you write cosine of 8 times t over 5 times cosine of t, and sine of 8 times t over 5 times sine of t, where t is from 0 to 10 pi. Now the only difference is that with polar plots, Maple knows, okay, the expression has to be interpreted as a polar curve. Here, if I use this bracket here, okay, Maple knows, okay, this expression is a parametric curve, so it has to be interpreted as a parametric curve, but the answer should be the same. No? Why not? Because this here. Okay, but the answer is the same, okay? So actually, it would not be necessary to have your own comment in order to plot polar curves, but of course it's more convenient to have a known comment. Actually, also the usual plot in Maple is able to plot polar curves by adding at the end chords is equal to polar. Then Maple knows that the curve has to be interpreted as a polar curve. So for instance, if you have given this polar curve here, assume a polar curve is given like this here, and the task is to convert here the polar equation into the Cartesian equation. Okay, so for instance, for this case, how do you do it? So here you see, okay, that you can write this here as 2 plus cosine, 2 times cosine of theta. Okay, so you see that r square is equal to 2 times r plus 2r cosine of theta. Okay, so now you get already this, because we want to have Cartesian coordinates. So we have here 2r plus, and this for this here you can write 2x. Okay, and for the r square here you can write, so this r square is equal to x square plus y square. So x square plus y square is equal to 2r plus 2x, or 2r is equal to x square plus y square minus 2x. And now you square everything and you get 4 r square, which is equal to 4x square plus y square is equal to x square plus y square minus 2x square. Okay, so the polar curve, this here is the polar curve, and this is the curve in Cartesian coordinates. Of course, this is only one direction, so I just proved that this polar curve lies on this curve here, but maybe it's not equal. Okay, for equal, I have to show. Okay, I can go in the other direction, similar as before. So you see that, but also this we cannot visualize it, so we do not understand how this curve looks like. But this is just the way how you can convert from polar curves into Cartesian curves. Of course, the other way around is also possible. So, for instance, if you want to know, okay, you have the parabola. Okay, now, how does the parabola? So this is in Cartesian coordinates. If you change to polar coordinates, what is the corresponding expression? Or what is the corresponding equation? So you plug in for y r square times sine square of theta is equal to r times the cosine of theta. Okay, so you see that if we delete r, so what you get is r is equal to 1 over sine square of theta. So this can be written as the cosecant of theta times the cotangent of theta. Okay, so this curve here would be a parabola, but in polar coordinates. And indeed, you can show, okay, this, in both directions, this is satisfied. Okay, so this curve here in polar coordinates describes the parabola. So you see that for a circle, okay, for some curves, like the circle, in polar coordinates, the expression gets much more simpler. Okay, so if you have a circle, x squared plus y squared is equal to 1, which is quite a complicated, you can say quite a complicated equation in Cartesian coordinates. If you change to polar coordinates, get very easy, r is equal to 1. Okay, but for instance, for the parabola, the Cartesian equation is much simpler than the polar equation. Okay, so for some curves, it makes sense to change to polar coordinates. For others, not. Also here in this case, you see if this curve would be much more complicated, or the equation looks much more complicated in Cartesian coordinates, but it becomes much simpler in polar coordinates. And the cardioid is another example, and so on. So in some situations, it's better to look at polar coordinates. In other situations, it's better to stick to our usual Cartesian coordinates. What is still left, what we will do next time, is for a polar curve. Given a polar curve, we want to figure out, okay, how to compute tangents, how to compute areas enclosed by polar curves, how to compute the arc lengths of a polar curve, and so on and so forth.